The t-test is basically a tool for us to compare the means, the point value estimates, the middle of two different groups, right? One group with a value, but usually two populate, comparing two things really, right? There's a few different situations that we might get into. One of them is when we have a known mean for an entire population, right? We know what that population is, but then we have another population that we want to compare to that to see if it's the same mean for that population, but we don't have any data on that population, so we're forced to take a sample. Rather than survey everybody, we have to take a sample. So we might go there and take a sample of, say, 50 people, 100 people, and we might use our sample to determine the mean of our sample and the standard deviation of our sample. And our hope is that the mean of the sample is similar to the population mean, and the standard deviation of the sample is similar to the population standard deviation. Based on that information, we get to kind of make a judgment as to where the true mean might be. That's how that's where we go into calculating a confidence interval. This is the average we got for the sample, but we're 95% sure, based on the variability in our sample, that the true mean lies between these two numbers, our confidence interval. And how do we do that? We do that by understanding how samples work and by calculating something called a standard error, which is the standard deviation of all the samples you might take of that size. So we know how variable we would expect samples of that size to be. So then we look at that range and we say to ourselves, well, we're 95% sure the sample for the population A is within these two numbers. And then we look at the known mean for population B, and we look to see if it's between those two numbers. And if it isn't between those two numbers, we say to ourselves, it's reasonable for us to say that the true mean of population A, based on that range, is different than the true mean of population B, which is outside that range. And depending on the width of that range, whether we want 95% confidence or 99% confidence, right, that's going to be a wider or narrower range. So, but that we have to make sure our mean is outside of that. That's called a single sample t-test when we do that. We're really using a confidence interval, the way I described it now, and seeing if our mean is inside or outside of that. But in a sense, that's also what we call a t-test. If we were doing an actual t-test, what we would do mathematically is we would look at the difference between our mean and our average for our sample, and we would subtract one from the other. Remember, x bar minus mu, just like we've done for a lot of other stuff, right? Like our normal distribution. So we would say, take the sample mean and the population mean, subtract them. That's the top of our fraction, our score, our t-score, our z-score, right? That's the top. And on the bottom is going to be what we would expect to be the range of samples, how many standard deviations or standard errors apart if we repeatedly sampled from that population that these values are. And we know that, just like with confidence interval, that if we're more than 1.96 standard deviations or standard errors in the case of the t-score or z-score, standard errors apart or samples, standard errors apart from 1.96 is a very, very, very large sample, then we can say if we're more than 1.96 standard deviations apart, we can say that the mean of this population is different from the mean of that population. Okay? If our sample is small, we're less certain about the variability. So instead of 1.96, we use a larger number to determine whether or not they're far enough apart. We use the t-score instead of the z-score. So if the sample size is 16, I'm working from memory here. If the sample size is 16, we use the value 2.103 for the t-score, that they have to be apart in order to say that they're different enough, because we want that extra margin of error for a small sample. Now, I just described the way we would do it for a single sample t-test. Known mean and a single sample that we take. Okay, now, a lot of times, most of the time in fact, we're not dealing with single sample. We don't know the mean of either population. So we need to sample population B, population A, and population B, and we need to really look at both of those and see if they're far enough apart. And in order to do that, we are going to do the same thing. We're going to look at the difference. I'm going to show you these formulas here. For instance, this first variation of the two-sample t-test assumes that the standard deviations of the two groups are equal. Okay, that happens a lot because if I ask you to compare the blood pressure of Mexican Americans to the blood pressure of Native Americans, right? Well, maybe one group has a higher average blood pressure than the other group, but it's reasonable to assume maybe the variation in blood pressures is the same. In other words, the range that you would expect around that mean is not that different. Maybe we wouldn't expect a low and high to be any further apart from one group than the other, but maybe the mean might be different. So a lot of times we'll be in that situation, and there's ways for us to test whether that's appropriate or not. So we're in that situation. We use, here we are, here it is down here. We use x1, the mean 1 minus the mean 2. Remember, there's no mu here because we don't know mu for either population. We just know the sample means. The mean of sample 1 minus mean of sample 2, and we divide that by the standard error. Now, when we have equal means, equal variance in the two groups, when we have equal variance, standard deviation in one group is similar to the standard deviation in the other group, it makes sense that we can help ourselves out by combining the values for both groups to calculate a single standard deviation. That makes it more accurate than just looking at them as two separate different standard deviations, right? So what we're doing basically is we're melding them together into a pooled standard deviation. And the way we calculate the pooled standard deviation is right here. It's going to be equal to the square root of the sample size 1 minus 1, the sample size of group 1 minus 1 times the standard deviation squared plus the size of sample 2 minus 1 times the standard deviation of group 2 squared divided by the sum of the two groups, the two sample sizes minus 2. Okay, and we take the square root of all that, and that gives us something that we call the pooled standard deviation. That's why that SP is there, pooled standard deviation. Well, remember, that's still a standard deviation. It's not a standard error. That's a standard deviation that's pooled for the two samples. Okay, so now the standard error based on that is found using this formula, which is basically kind of a weighted average. Standard deviation, the standard deviation pooled, I got an old version of this. This should be a P down here. Standard deviation pooled squared over N1 plus standard deviation over N2, and you take the square root, you add those two together, take the square root of the whole thing. So that will give us, it's the same thing, the difference between the means over the standard error. It gives us a value of t. How big t is tells us are they far enough apart, x1 and x2, are they far enough apart to say that these two groups have the means of the two populations are different, right? Are they really far enough apart? Well, the reason why we use t there instead of z is because based on the sample sizes, if it's a really big sample size for the two groups, we might say, let's use the z-score, 1.96, to be 95% certain that they're far enough apart, right? But if they're a small sample, what we do is we add up the two sample sizes and subtract 2. Let's say it's 10 and 10. 10 plus 10 is 20 minus 2 is the sample size of 18. We go to the t-table, look up what the t-value has to be for us to reject the null hypothesis with a sample size of 18, which happens to be 17 degrees of freedom, which is what they use there. Look up that t-value. I'm going to, just off the top of my head, let's say it's 2.09, right? And then I'm going to take that 2.09 and compare it to my t-score. And if my t-score that I calculated is bigger than 2.09, I can say with 95% certainty, or less than 5% chance of being wrong, that the two means are different from one another, and reject my null hypothesis and accept my alternative hypothesis. Remember, the null hypothesis is usually that they're equal. Okay, so that's one variation we might have. The second variation is where the two standard deviations are different for the two groups, and we don't feel comfortable just throwing them in together into a pooled standard deviation. Yes?
That's one question.
Yes?
The standard deviations have to be equal or the same number, right? In order to
The question was, I'm repeating because I want them here. The standard deviations have to be equal or close to equal in order to pool the standard deviations. I'm repeating what you're saying. I'm not agreeing with it quite yet. They don't have to be exactly equal. As a general, there's ways to calculate whether or not you can legitimately do this. In fact, SPSS does a specific test for this, right, to help you decide. In general, if we're doing the calculation manually, If one is less than twice the other, they're close enough. In other words, if the standard deviation of one group is 10 and the other is 18, okay, let's go ahead and do it that way. If the standard deviation of one is 30 and the other is 11, we start to say to ourselves, maybe we can't really trust that assumption. Okay, so if you're doing it manually, if they're within, within double or half of the other, if one is within double or half of the other, then I'd be comfortable just doing this for our purposes, right? So it gets more complicated than that, but for our purpose, in SPSS, I'm going to show you how to tell whether or not you can do that legitimately or not. It actually does a statistical test to let you know how certain you are that based on these two standard deviations in the sample size, whether or not you can, with some reliability, with again 95% certainty, say that the standard deviations are equal or not. So we're going to do it that way. But if you don't have that situation and one is more than half the other, less than half the other, or more than double the other, then you consider them not to be equal and you use this version of the formula. But again, look, it's the same. It's the difference to the two means on top, and it's the standard error on the bottom. Except this time the standard error is just the standard deviation of sample 1 squared, standard deviation plus over the sample size, plus the standard deviation of sample 2 squared over the sample size, add them together, take square root, and that's our standard error. Again, we're dividing our standard error into our difference between the two means. That gives us our t-score, and depending on the degrees of freedom, we can decide whether or not that t-score is big enough or not. How do we go? Now, there's one little curveball here. Now we have to determine what the degrees of freedom are. Before, when they were assuming equal variances, it was just add them together, n1 plus n2 minus 2. Now let's take a look at it. Now the degrees of freedom is equal to alphabet soup, right? It's that long formula. So if we look at that, that's going to be kind of tedious to actually calculate. So for our purposes, right, rather than use that when we calculate it manually, if you want, you can, for our purposes, you can say that the degrees of freedom is equal to the sample size of the smaller group. In other words, if you have 10 and the other one's 23, you can say that is equal to 10. I don't think it can be less than both groups. I think 10 is safe. I've said in some books it might say this is smaller sample size, -1 or -2, but I think you're okay with just the sample size of the smallest group. So then you can just use that to look up on your t-table what your critical value of t is for that number of degrees of freedom, and you can compare the two. Okay, you guys comfortable with that so far? Does it make sense? I mean, it's really just a little bit of math or algebra, right, at this stage. So what's the next possibility? The next possibility is if we're comparing two proportions. Well, where might that happen? Well, that might happen when you're trying to figure out whether the population of Queens has a different rate of diabetes than the population of Jamaica, let's say, right? So we're not going to go test everybody on that island and both islands. Queens, basically Queens and Jamaica, both islands, right? So we're not going to go to both of those islands and survey everybody and test everybody on both islands, but you might sample 50 people randomly in Queens, 50 people randomly in Jamaica to see, are you diabetic, are you not diabetic? Okay, so let's say we get 15% of people in Queens say they're diabetic, and 18% of people in Jamaica say they're diabetic. Well, now they're different, as we would expect. If the real rate, if we had sampled everybody in Queens and everybody in Jamaica, we wouldn't expect those two numbers to be exactly the same anyway, right? Because we'd expect a little bit of variation, right? So we kind of like are saying to ourselves, well, are our two samples, 15% and 18%, are they far enough apart that we can say reliably, 95% certainty, or 5% less than 5% chance of being wrong, alpha equals 0.05, right? Are we comfortable saying that the two proportions, the 15% and the 19%, are different enough? I think I said 18, but let's call it 19 for now. 19% are different enough that I can say that the proportions for the entire populations of Queens and Jamaica are really different from one another. Okay, and how do we do that? We do it exactly the same way. On the top, we look at the difference. Instead of x bar minus x bar 1 minus x bar 2, we have proportion 1 minus proportion 2, right? And underneath it, we have basically a measure of the standard error for those two proportions. Okay, so this represents a measurement of standard error, and the top measurement represents a difference in the two proportions, just like we did before. The difference between the two sample means over the standard error gives us a t-score or a z-score. How come this one says z instead of t? Anyone want to hazard a guess? If you go down somewhere in here, it may not be on here, but this process with proportion assumes that you have a certain sample size. And not only assumes you have a certain sample size, but it assumes that the proportion of people on each side of like diabetes, yes or no, it's not just that you have to have a sample of size 30, right, for Queens, but you have to have a minimum of 15 people in each side of the yes or no in Queens. So you have to have at least 15 people that say, yes, I'm diabetic, right? And then you'll have, obviously, if it's 15%, you'll have more that say they're not, right? So our sample size has special rules here. So the special rules wind up forcing you to use larger sample size than you did when you sample the mean, right? So because of that reason, a lot of times when we're doing this without using software, right, without using specific software, we'll use Z instead of T. If we use Z instead of T and we have an alpha of 0.05, what does Z have to be equal to for us to reject the null hypothesis? Remember, it's a Z now, right? We want to be 95% sure. What does Z have to be equal to? It's got to be equal to 1.96, right? That's our 95% confidence interval. It's always 95%, right? So you guys comfortable with that? You get the idea here, what's going on here?
Can you explain what you mean by it has to be like above 1.96?
Right. I'm going to draw that in a second. Well, one of the things I wanted to mention, though, was, see, this is looking at the difference between two proportions. We had a question earlier that talked about the election. Let's talk about that. Okay. Okay. I don't need that. Good. Recent. Okay. Okay. Let's say we poll people, and it looks, what did I do there? Say it looks like one candidate has, I use P cap to represent a sample proportion. It looks like we poll 300 people, and out of those 300 people, 140 say that they're going to vote for candidate A. So 140 divided by 30 is, should be able to do this in my head, but it's a long day today. 130 divided by 300. Did I say 130? 140, yeah. 140 divided by 300. I swear, I hate using a calculator on the computer. It's so awkward. Divided by 300 equals, that proportion is equal to 0.47. I'm going to call it 0.47, right? So the proportion for my sample is 0.47, right? 47% of the people in our sample say they're going to vote for person X, right? So now what we're really interested in, what the P is, the real proportion for the whole voting population is instead, right? That we're not really interested in our 300 people. We're interested in the entire population. So we want to know, how well do we understand this true point value? How good does it actually approximate what the true proportion is of people that are going to vote for this person? Okay, well, how are we going to do that? Well, we're going to set up a confidence interval, right? So what's our confidence interval going to be equal to? Our confidence interval is going to be equal to P cap plus or minus, well, I'm going to use 1.96. Why am I going to use 1.96? Because not because we know the population proportion, which we really would need to know the real value there, but because the sample is so big that I'm going to go ahead and use Z. If we're up in the hundreds, it's so close to, if you look at the Z table, as you go down the Z table, you'll see that the T table, as you go down the T table, the Z value, if it's a sample size of 10, it might be 2.2. A sample size of 20, it might be 2.05. Sample size of 30, it might be 2.01. Sample size of 100 might be 1.98. Sample size of 500 might be 1.99 and 1.97. So eventually it's going to get to 1.96. So big enough sample size, I'm just going to use Z. The Z value represents 95% of the possible outcomes. What happened there? Did I drop out there? Oh, went to sleep. That's interesting. Okay, so, and what is that going to be multiplied by? It's going to be multiplied by the standard error, the variability that we have for samples of proportions like this. So how do I calculate the standard error when I have a proportion? You guys remember that? The square root of P times 1 minus P over N. Okay, so what's that going to be equal to? It's equal to 0.47 times 0.53 over 300, and I'm going to take the square root of that whole thing. My pen is wearing out over here. That's why it looks so ugly. Okay, so let's get the calculator out again. Figure out what that variability is. Okay, it's equal to, remember, this is the standard error, 0.47 times 0.53 divided by 300 equals this, and then I'm going to take the square root of that. And it comes out to be 0.0, I'm going to call it 3%, 0.03. That's equal to 0.03. Okay, so what is it? It's going to be 0.47 plus or minus 1.96 times 0.3. So 1.9 is roughly 2 times 3 is 0.06. So it's 0.47 plus or minus 0.06, which means that my 95% confidence interval is 0.41 to 0.53, right? Can I say that this person's going to win this election or lose this election? No, because 50% is within this range, right? So I can't say I'm more than 95% certain that this person's value, that the outcome for this person is going to be over 50% or under 50%, right? So now, the way that, what do we call it? You guys remember what we call this part over here that you're adding and subtracting?
Margin of error.
Exactly, that's the margin of error. Now, if you ever notice that when you see a political poll and it says, oh, okay, this person's got 47% of the vote, this person's got 30% of the vote, this person's got 10% of the vote, but they always say plus or minus 3%, right? Well, the p-values for each of these are different. How could it be the same margin of error? They do something very tricky. They go over here and it's in p and 1 minus p. Instead of using the actual proportion like 30%, they use the value 0.5. The value 0.5 is the biggest number that you can get for the standard of error. Anything but 0.5 is going to be a smaller standard of error. 0.5 times 0.5 is 0.25, right? 0.4 times 0.6 is 0.24. 0.3 times 0.7 is 0.2. Since he has the bigger spread is, the smaller the number is. So they're just using the biggest number so that they conveniently can just say the margin of error on this poll for everybody is 3%. They're kind of fudging it a bit. Okay, so now how did things go wrong on Tuesday, right? Well, let's take a look. When they take a poll, they're polling, let's say we're just going to look at New York State. They poll people in New York State, and they randomly call, I'm presuming, let's say it's a phone poll. They randomly call people all over New York State. They might go county by county. And they might call 100 people in Queens, but only 20 people in Westchester. Why is that? They're collecting data in relation to the populations in those counties, right? They want to see what's happening all over the state. They want to make sure that it's representative of New York, they don't want to poll 100 people in Westchester, 100 people in Queens, but then because then they're overestimating the vote in Queens, the outcome of the vote in Queens. That's one thing. So the first thing they do is geographically they try and randomly pick people so that they're reflecting the geographic population centers around the state. Okay, what's the next thing? Let's say that in New York, let's say the population of New York State is 51% women. So let's say that when they take their random samples, a lot of people don't answer. You know, I don't pick up my phone. I don't know about you, right? I have a landline still. Old people like me still have landlines, but I never answer it. So I don't know why I don't have a landline anymore. But let's say that that I don't answer my phone. So, you know, they'll miss me in that polling, right? So at the end of the day, they see that they take all their numbers, they've sampled 1,000 people from all over New York State, and they find that, you know, should be 510 of them should be women, right? So maybe, let's see, 510 are women, but we only have 500 women in the polls, 500 males and females. They adjust the poll, they weight the poll to overweight the women that did respond, so they represent 51% of the population. What else do? They do the same thing for the registered Are you a registered Democrat, registered Republican? If it's not weighted right in their polling, they reweight the responses. So in other words, if not enough Republicans replied, they count their votes more than the Democrats to make sure that the polling represents the people that are really out there, right? So that's what they do. And a lot of these polling groups, their weighting is supposedly based on science, figuring out whether or not their sampling really is representative, and they make the adjustments. One of the things they have a lot of problems making the adjustment on this time is whether or not a person came out to vote. And it turns out that people came out to vote in rural areas that tended to be more Trump supporters and more Republican at a higher percentage than they ever did before, right? So in other words, if you had 100 voters, every other year in this area, you'd get between 30 and 70, 30 and 50 of those people coming out to vote. This time they were getting 60 or 70 coming out to vote. So what happened was they based their weighting for what the voting rates would be in all these different counties based on historical records of those, historically how those counties had gotten out to vote, right? Not really on the data that people were giving them on whether or not they were really going to vote or other indications that they had. And there was only one group that actually got pretty close to the real totals because they actually saw this data was kind of curving away from the expected values for the voter rates, and they actually went with the science, the math, rather than historical voting patterns, right? In other words, what they were getting today, rather than the few days before the election, the information they're collecting a few days before the election, rather than historically how these different groups voted. That's why you had so many of them getting it wrong and only a couple of them getting it right. So it was all about the weighting, right? How random it is, the math, the science. It gives you what we're doing now. It's a way for you to understand the probabilities. In other words, when they said if it was just a random sample and it was done as a random sample, then the probabilities would be right on. The probability would be plus or minus 3%, or plus or minus 5%, or plus or minus 1.5%, right? But the problem is in sampling, you always wind up very frequently you wind up with a sample that's skewed in one way or another. Too many women, too many men, too many Republicans, because of the nature of sampling and responses and stuff like that. So you have to figure out how you should weight that, how you should handle that data, so that what you get is really representative of the population. In other words, take out confounding factors. And a lot of studies have confounding factors. Like, for instance, you do studies on cancer, right? You want to make sure that the group A doesn't have more smokers than group B. Why is that? Because it's associated with cancer and so on. So that's one of the reasons why this kind of got messed up a bit. And really it's partly because they didn't go with the science. They went with historical data rather than the real numbers they were collecting now. But so it's really complicated. This whole thing is very, very complicated. right? This whole deal of how they would do this. Okay, so let's take a look at homework number. I'm gonna cancel. I'm gonna minimize this for now. Let's take a look at I put up 2 homeworks. One of them strictly confidence intervals and single sample t-test. 5B starts with a single sample t-test and then moves on to like two sample t-tests. Let me bring that up. I made both of these due not this Monday, but the following Monday, I think. And I'm getting ready to put together a test. I'll give you some heads up on it. But I'm thinking maybe I'll give you over the Thanksgiving Day weekend after Thanksgiving, like Friday or Saturday, I'll post it. So you'll have the following week to do it. Okay, that way, if those of you that want to work on it over the holiday, you can. If you don't want to work on it over the holiday, you have the week after. Okay, let's go in here. Independent samples.
I'm just looking at, you didn't change the due date for assignment 5.
Oh, it's still, yeah, I'll go back to him. It's the 20, what does it say, the 14th or something?
5 is on the 14th and 5 days.
Okay. When's the 14th? It's coming Monday?
Yeah.
Okay, I'll change them so they're about the same date. Actually, I would encourage you to do them by the 14th anyway, but I'll change the date so I don't get people freaking out because not that many people have worked on it yet. Okay? Where I can, I try to avoid people raising student blood pressures. Okay, not always possible, but I can do my best. The mean citywide exam score of population of first-year students, high school students, is mu is equal to 600. So we know the population mean there, right? We know that the mean citywide exam score for this exam is 600 for all students in the city, right? We all got that? An investigator wants to test if the mean SAT score for first-year psychology students is significantly different than the mean for everybody. Okay, so how's he going to do that? Well, he needs to go and sample these psych students. So he goes and randomly selects 100 psych students, sample size is 100, and he finds that the mean for that sample, X bar, is equal to 624, looks like they had higher scores, okay, and the standard deviation for that sample is 100. Okay, so what kind of t-test is this going to be? Is it going to be a single sample t-test, or is it going to be a 2-sample t-test, or equal variances, unequal variances? How many samples did we take here? Only 1. No, we had to write the mean. We know the mean of the population, right? Okay, it's only 1 sample involved here, right? So we're going to compare this mean to mu. Okay, so say your null and alternative hypothesis, right? Remember now, the null hypothesis only has to do with the means of the 2 populations. It is true that we don't know the mean of one of these populations, and we only have the sample mean, but we're using that sample mean to predict whether the means are different. So we're always talking about the means, not X bar. So it's always going to be mu equals mu population equals mu psych. Mu population does not equals mu psych students. Mu population is less than or equal to mu psych students, or none of the above. So which one do you think that is? Right? The null hypothesis always has an equality in it. Right? So right now, our null hypothesis we're starting with is that the mean of the population is equal to the mean of the psych students. That's it, right? We're going to start with the assumption that they're the same so that we can disprove it and say that they're different. Okay, are you comfortable with that? Okay, good. Okay, calculate the value of the standard error for the means of sample size 100 for psych students. Okay, well, okay, our standard deviation is 100, and our sample size, our standard deviation is 100, and our sample size is 100. So what's the standard error for this sample going to be? Okay, I'm going to pull this back up again. Oops, wrong. Let me move this out of the way. Let me get this back. Okay, look at the first page here. So let me summarize all these numbers here. Okay, so mu for the entire population, all output, is equal to 600. X bar for a sample is equal to 624. And the standard deviation is equal to 100, and the sample size is equal to 100. So what's our standard error equal to? How do we calculate standard error? It's sigma over the square root of n. Do we know sigma? We don't, but we know s, right? So we're going to use s. 100 over the square root of 100, which is 10. So this is equal to 100 over 10 is equal to 10. So our standard error is equal to 10. Okay, so now, I'm going to go back here. Okay, so you would put 10 in here, right? Okay, so now I'm going to go back here and I'm going to say, what's the next question? Calculate the value of the t-score, t or z-score, you choose which is appropriate, based on whether the population or sample distribution is known for the above problem. Okay, now we don't know the population standard deviation. We don't know the population standard deviation, sigma, for psych students. We only know S. We don't know sigma. We don't know what it is for all psych students. We only know for our sample. So really, we should use T. Now, there would be a lot of people that argue, well, gee, 100's a big sample. Let's just use 1.96. For our purposes, let's stick with the t-score because it's just a little bit different. We'll see that in a second. So what is the t-score going to be equal to? What's our formula for that? X bar minus mu, the difference between the two means, divided by the standard error. What's that going to be equal to? It's equal to 24 divided by 10. It's equal to 2.4. Okay, so now we have to decide, is that t-score big enough for us to say that mu1 does not equal mu2, right? Is that big enough? So what does the t-score have to be? What determines how big the t-score has to be to do that? It's going to be the sample size, degrees of freedom. So let's get up our table, the t-table. Oops. I think I have it here somewhere. Oh, no, this is something else. Try again. Oh, let's see. I see what happened here. T-table. There we go. Okay, so let's look at it for 100. Okay, so I'm going to go down here. Okay, what we're interested in is 5% chance of being wrong, which is the same as a 95% chance of likelihood that we're right. Right, 95% confidence interval. In other words, 2.5% in the right tail, 2.5% in the left tail. I'll take a look at that later on. Notice how the sample size, actually degrees of freedom, it's going to be 1 minus, so we're looking for 99. But notice how the t-score gets smaller and smaller and smaller until it's equal to 1.96 when you get a really big sample. Okay, but for a sample size of 100, 99, they don't have 99, so I'm just going to use 100. It's not 1.96, it's 1.98. So our critical value of t is 1.98. Our two means have to be 1.98 standard errors apart. That's what t-scores basically is. Standard errors apart for us to reject the null hypothesis with less than 5% chance of being wrong. So our critical value of t, so if I'm going to, the t-value in here is going to be equal to 2.4. Calculate p-value for this hypothesis test, and so on and so forth. Well, I just decided that the critical value is smaller than the t that I got, so I can reject my null hypothesis. It also says calculate the p-value, the probability of being wrong in this situation. Hint, using Excel equals t-dist, t-value, degrees of freedom, and tails. I'm going to pull up Excel and show you what I mean by that. You could just go with the t-score that we calculated and the critical value of t. And since your 2.4 was bigger than 1.98, you can say I reject the null hypothesis with an error of less than alpha is equal to 0.05. Our probability of being wrong is less than 0.05. So I'm going to do this another way, and I'm just going to open this up here. And if I type in here equals let me see if there's another one. If this, I can actually blow this up even more so you can see it better. Okay, equals t-dist parentheses. Notice when I put the parentheses in, boy, everything is blown up except the part I want you to see. That's totally unaffected. Okay, t-dist is value x. That's really t that they're talking about there, comma, degrees of freedom, and tails. So in our case, what did we calculate t was equal to? 2.4, right? Comma, degrees of freedom, sample size was 100, this is going to be 99, comma, and tails. It's a two-tailed test, meaning that we didn't make a judgment ahead of time whether the mean for psych students was bigger or smaller. We just were interested in different. Right? So it's two-tailed test. Okay, I'm going to hit enter and see what the p-value is. The probability of being wrong, the p-value, is 0.018. It's about a little under 2%. What is our alpha value? Was 0.05. We will tolerate up to 5% chance of being wrong. When we have a t-score of 2.4, our chances of being wrong is only 2%. Actually 1.8%, 1.018, right? So we reject the null hypothesis. You could reject the null hypothesis because the p-score is less than 5%, or you could reject it because the t-value is bigger than your critical value of t. And the bigger that t is, watch what happens if I put in a bigger value for t. Make it if I put in a value of 3.4 for t, is that number going to get bigger or smaller? Probability of being wrong. They're further apart. That probability of being wrong is going to go down, right? And there it goes. Once I got up that high, 3 standard deviations apart, 3 standard errors apart, it got to be very small. Okay, so let's see what do we do here? What's the result? You accept the null hypothesis, you reject the null hypothesis, you reject the null hypothesis and accept the alternative hypothesis, you accept the null hypothesis and reject the alternative hypothesis. What do you guys think the answer there is? You reject the null hypothesis and you accept the alternative hypothesis. Remember, the alternative hypothesis was that they were different. You reject the null, which you started with, right? So you see the idea here is you start with they're equal, and then you use statistics to prove that they're different given a certain amount of probability, of course. Okay, so let's say our t-score came out to be 1.8. Could you reject the null hypothesis? 1.8 is smaller than your critical value of t, which was 1.98, right? So you can't reject the null hypothesis. So what do you say in that case? Do you accept the null hypothesis? Kind of, you would think that, right? No, you never say that because you really haven't proved anything. What you do is you say, we failed to reject the null hypothesis. Whole idea was you wanted to be able to reject the null hypothesis that they were equal and accept the alternative. If you don't have the evidence to do it, all you say is, I failed to reject the null hypothesis, right? You haven't really proved anything, okay? At least not to the statistical level, the level of certainty that we want. Okay, let me just check to see if there's any questions there. I don't see any questions. And let's see who we got back here. Hi, Ben. Hi, Carrie. Okay, if you got questions, type them in there. Okay, so let's move on from there. Okay, this should give you a boost on these problems anyway. Okay, now let's take a look at this one. A study was conducted to determine if expectant mother's cigarette smoking has an effect on the bone mineral content of her otherwise healthy infants. I gotta reduce the size of this a bit so I can fit it in here. Oops, that didn't help. Let me open this a little wider and spread this off. Spread this out here. Study was conducted. I'm not sure why this is not wrapping. You would think it would, right? No, Blackboard's a very strange program. Study was conducted to determine if expectant mother's cigarette smoke has effect on the bone mineral content of her otherwise healthy baby. A sample of 77 newborns whose mother smoked have a mean mineral content of 0.99 grams per centimeter and a standard deviation of 0.026 grams per centimeter. So what do we have there? We have a sample. Sample size is 77. So our mean X bar 1 smokers is 0.099 with a standard deviation of 0.026. A sample of 161 newborns whose mothers did not smoke, different sample, sample 2, have a mean bone mineral content of 0.091 grams per centimeter with a standard deviation of 0.025. Assume that the variances of the underlying populations are equal. Is that a good guess? Does it look like they're equal? What was one? 0.026. The other one was 0.025. What was our general rule? If one is not double the other, then you can kind of assume they're close enough to say equal, right? And pool them. Okay, so state your null hypothesis. What would your null hypothesis be here? You guys want to pick one? Right? What are our choices here? The mean for smokers is not equal to the mean for non-smokers. The mean for smokers equals the mean for non-smokers. Mean for smokers is less than or equal to the mean for non-smokers, or none of the above. Right? Mu smokers equals mu non-smokers. The two means are equal to one another. Okay, state your alternative hypothesis. What's our alternative hypothesis? What are we trying to prove? Right? The mean for smokers does not equal the mean for non-smokers. So we start with our null hypothesis that the two means are equal for the two groups, and we want to prove the alternative, which is the mean for smokers is not equal to non-smokers. That's almost always the way it's going to be. Every once in a while, you'll come across a situation where you'll see something like the mean for smokers is less than, for the null hypothesis, less than or equal to the mean for non-smokers. The equality is always in the null hypothesis. What does that say? That says that, I don't think it's even possible for the mean for smokers to be greater than non-smokers. So I'm going to call this a one-sided test. I'm not going to have you play with one-sided tests right now. Later on, as we get into the semester and we look at some other data, when we start talking about whether you want to take an exam or a project or something like that, it'll come up for the project kind of stuff. And we'll talk about single-sided t-tests, where you're willing to make the assumption that it can only be, if there's a difference, it can only be in one direction. Why is that an advantage? The reason why that's an advantage, remember I referred to this as a two-tailed test. I referred to it as a two-tailed test because if I start with a null hypothesis, which I want to prove that I want to be 95% certain that I can reject or have less than 5% chance of being wrong if I reject it. If I don't know if the mean of one group is bigger than or smaller than the other, I got to take that 5%, split it up into two, put 2.5% in one tail of the distribution, 2.5% in the other tail of the distribution. So what does that mean? That means you got to move your range outwards, right? So it's harder. You get a bigger t-score, a bigger z-score that you need to go further out for a two-sided test, right? If I said one single-sided, I could say, let's put all 5% on one side of the distribution. Well, 5% is on one side of the distribution. Instead of having to be 1.96, it only has to be 1.64, right? Remember, that's the other value. Remember, we were talking about 1.64, 1.96, 2.58 for the standard z-scores that we would use for 90%, 95%, 99% confidence intervals. It doesn't have to be as far away. The means don't have to be as far apart with a single-sided t-test. The only problem with that is that you have to be able to justify that. And in fact, even if you could justify it, most of the time you'll go with a two-sided t-test anyway, because it's a more conservative approach, right? Everybody's going conservative these days, apparently. So that's the way the direction seems to be tilting. So, it's a more conservative approach, safer approach. Because at any rate, maybe not safer, but more conservative. At any rate, state your alternative hypothesis. Okay, what's our alternative hypothesis if we're doing a two-sided test like this? The mu for smokers does not equal the mu for non-smokers. We want to reject they're equal and accept the alternative that they're not equal. But to do that, we have to do our math down. Calculate the pooled standard without how. Remember, we now have exactly the situation that I talked about in that document, right? The first one for two sample t-tests. Where'd it go? Let's see, here we go. Okay, where is it? Okay, it's that first page. This is, how do we compare means of two populations? You can always bring this up. If you're working on the homework or whatever, you can just pull this up. It's on, on Blackboard. You got a newer version of this actually, which this one actually has a kind of a glitch in it because see these S1 and S1, that really should be SP and SP because you calculate the pooled standard deviation and then you plug it in there. Well, I want to be able to talk about another problem, what we would do with unequal variances. So I'm not going to actually solve this completely, but I'm going to talk about how to solve it. Okay, so what's the first thing I do is got to calculate this pooled standard deviation. So how do I calculate that? Well, let's see. What do I have there in my problem? let's go back to the problem, which says, okay, how many smokers did we have? We had 77 and a standard deviation of 0.26, 161 and a standard deviation of 0.025. Okay, so I want you guys to remember those two numbers for me, 77, 166. Okay, so let's go back to our sheet. So what is this pooled standard deviation going to be? Well, it's going to be equal to N1 minus 1, that's 77 minus 1, so you're going to put 76 in there, times the standard deviation squared for group 1. What is that? That's 0.025 times 0.025, or 0.026 times 0.026, right? Plus N2, which I think was 161, minus 1 makes it 160 times standard deviation 2 squared, which was 0.025 times 0.025, right? So we got those two numbers. We're going to add them together and divide by the sum of the two sample sizes, 77 and 161, which is going to give us 238, I think. Minus 2 is going to give us 236. So we're going to take that number divided by 236, and then we're going to take the square root of that entire mess, and that gives us our pooled standard deviation, right? Just plug it into the formulas, right? Not anything exotic, just remembering the standard deviation for sample 1, standard deviation for sample 2, and the sample sizes, and just figure that all out before you find the square root and then find the square root. Okay, so now what are we going to do? Well, then we're going to write that in here, right? Because that's the first thing it asks for. It asks for it asks you to calculate the pooled standard deviation. That's your first step anyway, because you need to calculate that in order to calculate the standard error. The standard error is this bottom part down here. We didn't call it standard error, but that's what it is, right? It's going to be the square root of the pooled standard deviation. Your version actually has a p there. Pooled standard deviation squared over n1, 77, plus the pooled standard deviation 2, same number, right, as you calculated there, over the sample size 2, which was 161, add them together, find the square root of the sum of those two things, and then you look at this, okay, then we put that in there, that's going to be your standard error. You're going to plug the standard error in there. Now calculate the t-value for the difference between the two means. Well, the t-value is going to be equal to x bar 1 minus x bar 2, which was 0.099 minus 0.091, I think. So it's going to be 0.008. So this is 0.008 divided by the standard error, okay, which I'm going to take a wild guess and say it comes out to like 0.03 or something like that. I think that's my recollection. Okay, so it's 0.009 divided by 0.003, a guess again. So the t-score, I'm going to say, let's say the t-score comes out to be 3, right? You're going to write whatever the t-score is in there. It probably isn't exactly 3, it's probably something else. You're going to write the t-score in there, right? Maybe 3, maybe not. And then it asks you to look up the critical value of t that you will need to exceed for alpha is equal to 0.05, less than 5% chance of being wrong. Okay, how do we find that critical value of t? Well, we go to our Grusty's t table. Do I have it open? So, yep, there it is. Okay, and we go down here 95%. Okay, and we go down to see, well, what's our sample size? Our sample size, if you go back to that page, remember what it was? That's the simple one. N1 plus N2, right, minus 2. So 71 and 77 and 161, 238 minus 2, 236. So it's going to be 236. Well, if I look over here, 1.98 is 100, right? So it's going to be like 1.97 maybe. You want to know something? It's so big that I'm just going to call it 1.96, like what we would call it if we knew, because it really is a big sample. It's over 300, right? So I'm going to call it 1.96. That's our critical value of t. That's what we have to exceed. So, okay, so I think that I programmed, actually I might call it 1.97 because it's not really quite 1.96. So, and you can actually use SPSS, Excel to actually calculate it. Okay, so now, let's see. So calculate value of t comes out to, let's say, whatever, 2, 2.5, 3, 2, or 3. What's the critical value? I'm going to call that 1.97. Okay, based on the above result, what's the most appropriate conclusion? Well, having told you that I think it's going to be, let's say it comes out to be 2.5, right? You've exceeded the critical value 1.96. So that means your p-value is going to be less than 0.05, going to be less than alpha, so you can reject the null hypothesis. A t-score bigger than the critical value of t, 2.5 versus 1.97, or a p-value less than alpha, less than 0.05, says that you can reject, tells you can reject the null hypothesis. Okay, so that's what you're going to do there. You're going to reject the null hypothesis. And what do we do when we reject the null hypothesis? We accept the alternative hypothesis. Okay? Okay, good. So, are we still breathing? Okay, anybody ready to, like, they have floor-to-ceiling windows here, no openable windows. So there's nobody's leaping out the window, right? It's not that hard, right? A little bit hard. Okay, good. No, a little bit hard's good. A little bit's hard, a little bit of a challenge, good. But yeah, what you were saying.
Yeah, I think I got it. My only question was, how did we calculate
The standard error is the bottom part. I didn't actually call it the standard error, right? But if you look at this, it's the bottom part. It's the denominator, right? Bottom parts of the top part's the numerator, bottom parts of the denominator, right? So that standard error is equal to. Remember that if you look at your version, that says S2P and S2P. They're both the same value, right? It's kind of like weighting the two of them. Okay, so that's the way you would calculate them. Yep. So now, what's the next thing that might happen? Well, the next thing that might happen is you might get a situation like this, where the values, that the standard deviations are not equal to one another, right? Like, for instance, let's say we had the same problem, exactly the same problem. 0.099 is one mean, 0.091 is the other mean. The standard deviation of one is 0.025. The standard deviation of the other is 0.010. Oh, it's less than half the other one. Well, the first one's 0.025, the other one's 0.010. It's less than half. Well, I don't think they're equal. I don't think I can justify saying that they're equal anymore. So in that case, we use the second page here, compare means of two populations. Standard deviations are not assumed to be equal. So how do you do that? We're going to do exactly the same thing. We're going to calculate t, except this is simpler in a way. It's the same as before. X1 minus the two means, the difference between the two means, that was 0.099 minus 0.091. It comes out to be 0.008, divided by the standard error, except this time the way we calculate the standard error is the standard error of the first group squared over the sample size of the first group, plus the standard error of the second group squared, so it'd be 0.025 over 77, plus 0.010 over squared over 161, right? And then you'd have to add those together. Hard, we do it by hand. It's going to be hard because you got a common denominator and stuff you need. But if you do it on the calculator, it actually comes out pretty easy. And you add those two together, and after you add them together, you take the square root, and that's your standard error. And you calculate a t-score just like before. And based on, now, what's your critical value of t based on? The degrees of freedom, the sample size. That's where things get complicated. You can either solve this formula to find the actual degrees of freedom, right? Or you can just say the degrees of freedom are equal to the smaller sample size. Okay, so I'll do that. I'll say the degrees of freedom are equal to 71. Maybe I'll say 71 minus 1, 70. Okay, now if I open up my t-table, for 70 degrees of freedom, right? In this case, my t-score has to exceed, let's see, somewhere between 2.2 and 1.99, right? So I'm going to choose 2.00. 2.00. Instead of 1.97 now, our critical value of t is 2.00. Right? I'm going to go more conservative because it's in between. So I'm going to be 2.00, right? So if the t-value that you calculate here is greater, if this t-score is greater than 2.00, you reject your null hypothesis and accept the alternative. If your t-score is less than 2.0, then you fail to reject your null hypothesis. Okay. Now, let's say we did this with Excel, with SPSS. Okay, now the next problem I have here is that rather than at this point make sure that, because I know a lot of people having issues with SPSS and so on and so forth. So what I did was I actually produced the table for comparing. If you look at the exercises that we did, the lab exercises for tonight's session, you'll see us actually work out a couple of problems where we solve, we compare two means using actual data in SPSS. And we wind up getting a table. We tell it analyze, compare means, independent samples, t-tests, and we tell it that this group and this group are the ones we want to compare. If you look at the video, you'll see how we produce this table. And SPSS produces this table. Okay, so now here's a table that SPSS has produced. And let's take a look at what it says. It says that, so I can't make this bigger. Okay, what does it say? The question is 100 male and female infants is tested to determine if there's a difference in systolic blood pressure with the following SPSS table. Based on this result, you would assume the variances of the two groups are they equal or unequal? How do they look? Here's the two groups. Here's 44 male, 56 female infants, and the means are this, but the standard deviation 11.8, 11.14. Would you say those are equal variances or unequal variances based on the rules that we were talking about? Is one double the other? No, they're pretty close, right? So I would say it's likely that they're going to be equal variances. You don't actually have to leave it up to guesswork when SPSS does this. SPSS, when you tell it to compare the means, it actually gives you a table, an independent samples test. It gives you a table, and in the beginning of this table, notice that there's two lines here. There's an upper line and there's a lower line. But before we get to the main part of this table, which is to the left of this line here, we have a box here where we have just two values. This is Levine's test for the equalities of variances. Okay, and our significance here, F is the value of this particular, they happen to call it F for whatever reason. That's the value of this particular statistic. Okay, but associated with that value, the bigger that number gets, the less likely that you're going to be wrong for rejecting the null hypothesis. In this case, what's the null hypothesis? That the variances are equal. Okay, so the bigger this F value gets, the less likely you'll be wrong if you reject the idea that they're equal and go to the bottom line where it says they're unequal, right? Okay, but how big does it have to be, that F score? Well, we don't have to worry about that because right next to it, it's got something called significance. That's the same thing as our p-value, or probability of being wrong if we reject them being equal. Well, what's the probability of being wrong? It's almost 80% probability of being wrong if we reject the null hypothesis, right? So that means we failed to reject the null hypothesis. So that means we should stick with the top line. Okay. So when this asks you, when the problem asks you, wherever the problem went, where'd it go? Oh, it's still here. It's in the same spot. When the problem asks you, based on the null hypothesis, would you say that the variances of the two groups are equal or unequal? You would type in equal there, right? Based on that Levine's test. Okay. The value of t for this test is, let's look at the table. What's the value of t? Is it 0.607 or 0.603? Which line do we use, the top one or the bottom? Right? We failed to reject that, so we're going to stick with the idea that they're equal. So we use the top line. So the value you should be typing in there is 0.607, not 0.603. Okay, so let me go back there. Okay, what's the next thing it asks for? The value of this t-test is, whatever it is, 0.607, with a p-value of, what's the probability of being wrong if we reject the null hypothesis? What's the p-value that, what is, my goodness. I want to try and get that to go away. Okay, maybe we don't need it to go away. Okay, so what is the p-value? Probability of being wrong if we reject the null hypothesis. Again, significance for the t-test now is over here. So what's the probability of being wrong? it's 0.54. It's much bigger than 0.05, right? So since it's smaller than 0.05, we fail to reject the null hypothesis, right? That's not that big a surprise, right? Why is that not that big a surprise that the p-value is so much bigger than 5%? Because the t-score is so small. We can almost see immediately that, oh, that t-value is too small for us for any critical value. The smallest critical value that we can have is 1.96, the same as the z-score. So that's way smaller than 1.96. So I'm not going to have a big enough t-value to be bigger than the critical value of t that I need. So similarly, the p-value is always going to be bigger than 0.05 in that case. Okay, so, and I think that's all that it asks for. That suggests we should fail to reject the null hypothesis. Reject or fail to reject. Fail to reject the null hypothesis. Okay, so, and now the last one here, let's take a look at what that one is. It's a very similar kind of situation, except this time, let's take a look at this. Okay, again, the significance, the F value of significance is very small, so we stick with the top row. What's the t-value? T-value is 4.476. What's the significance? The significance is not really zero. It's really less than 0.001. It means that it's less than 1/10 of 1% chance of being wrong if you reject the null hypothesis, right? And so, so you can use that to figure out what you're going to put into question 16.